Hi everyone, welcome to our lecture on root locus. This is a very important tool that will help us design controllers for dynamic systems. Essentially what root locus does is it tells us how the poles of the system move around as we increase the gain of the controller. There are tools out there, especially in MATLAB, that allow us to plot root locus very easily, but our objective in this course and in this lecture is to be able to plot root locus by hand. In order to do that, we will go through some very important features that will help us achieve that objective. We'll talk about those features first, and then we'll have some examples where I will show you how to use them to plot root locus for different functions by hand. If the features overwhelm you or make you confused a little bit, don't worry about it, because by the time we get to the examples, hopefully everything will clear up. Let's start our discussion by considering a very simple closed-loop system. A system that consists of a plant that I'm showing with a transfer function g of s, a feedback path that I'm showing with a transfer function h of s, and a very simple proportional controller that I'm showing with a constant gain of k. You remember that the transfer function of this overall system is the gain of the feed-forward path divided by 1 plus feed-forward gain times feedback gain. The gain of the feed-forward path in this example is k times g of s, because both of them are included in the feed-forward path. So the transfer function, which is the ratio of Laplace transform of the output y of s to the reference r of s, is going to be k times g divided by 1 plus k times g times h. This quantity g of s times h of s, by the way, is a very important quantity that is known often as loop gain or open loop gain. This is a term that will come up very frequently in our discussion about root locus or Bode plot. So remember that every time we talk about loop gain, we are in fact looking into the multiplication of the plant's transfer function g of s and the feedback loop transfer function h of s. Now again, you remember from our previous discussions that the roots of the denominator of the transfer function indicate the poles of the system. The closed loop poles of the system give us the most important information we need to know about the system. They indicate whether or not the system is stable, and they indicate if we apply a unit step or a unit ramp to the system, how fast the system will respond, how much rise time, overshoot, settling time. All these quantities are things that we find out by looking at the poles of the system. So that is the most important thing that we would like to know. In order to find the poles, I look at the denominator, and let me rewrite the denominator here. So I have 1 plus k times g of s times h of s equals 0. If I set it to 0 and find the roots are going to be the poles. That is simple enough, and this is something we have seen before. However, you notice something different here, that here I have a k. This k is a parameter. This is the gain of my controller. And as you can imagine, if I change the gain of the controller, the roots of this polynomial will change, and as a result, the closed loop poles of the system will change. So one natural question that comes to mind is, what closed loop poles can we get if we change the gain of the controller? And this is the question that root locus will try to answer. So based on what we saw, a value p is a pole of the system if it's the root of the denominator, meaning that 1 plus k times g of s times h of s is 0 if I set s to be equal to p, meaning that 1 plus k times g times h, both of which evaluated at p, would add to 0. I can rewrite that equation in the form of k times g times h equals -1. And -1, as you know, I can rewrite it as a vector with magnitude of 1 and angle of -180 or +180. Both of them indicate the same thing. So what we would like to know is, for different values of k, what p-values would satisfy this particular equation. Any p-value that would satisfy this equation would be a pole of the system. And by changing different k values, we would try to find different p values, which would be the changes, the variations in poles as a function of variations in controller gain. Okay, So as we change the gain k of the controller, the poles of the closed loop system will start moving around. Root locus is a graphical tool that will show us how and along what trajectories will these poles move around. And more importantly, do they move around while staying in the open left half plane, or do they start creeping into the right half plane, hence making the system unstable? One thing you have to remember is for a system that has n closed loop poles, each pole will start moving along a particular trajectory. Each trajectory is referred to as a branch or a locus. So root locus will give us multiple trajectories, multiple branches, multiple loci, indicating where the poles are moving around as I increase k from 0 to infinity. Before we get into the discussion of the features of root locus, let's clarify that through a very simple example. Let's say I have a system that consists of a constant gain controller and a double integrator, so 1 over s squared, and a unity feedback loop. So if I want to find the transfer function of the closed loop system, it's going to be the feed-forward gain, which in this case is k divided by s squared, divided by 1 plus k divided by s squared times h of s, which in this example is 1. If I multiply both the numerator and denominator by s squared, I will get k divided by s squared plus k. This system is a second-order system, and hence it has two poles. The poles of the closed-loop system are in fact the roots of the denominator, the roots of this polynomial s squared plus k. And here you can quickly see that the roots or the poles are going to be functions of k. So if I set the denominator to 0, s squared is going to be minus k, meaning that s is going to be plus minus j square root of k. So the poles are going to be directly functions of k, the gain of the controller. Let's try to see how these pole locations change as I start increasing k from 0 to infinity. So if k is 0, I will have two poles at 0. So both of them are going to be at the origin. Let's say k is 1. I will get two poles. One of them is plus j1, the other one is minus j1. So one pole will come here, the other pole will go here. If I set k to 2, one pole will be plus j square root of 2, let's say somewhere here, and the other one is going to be minus j square root of 2. The other one will be here. And you can see the pattern here. As I start increasing k, one of the poles will move along the j omega axis all the way towards infinity, and the other one will move along the j omega axis towards minus infinity. So if I use different colors, one of the branches is going to be this branch along j omega axis in this direction. The other one is going to be this branch that I'm showing with color green. This is a root locus for this very simple system. And it tells us that if you have this system consisting of a double integrator and try to control it with a proportional controller in a closed loop fashion, you will have two poles in the system that will move around along the j omega axis towards plus j infinity and minus j infinity. There are a few things that I want you to pay attention to here. Notice that the system has two poles because it's a second order system. And here you will see that the root locus also has two branches, one branch per pole. And each branch indicates the movement of one and only one pole. Of course, this is a very simple example, and as you will see later on, if we go to a more complicated system, the direction of the loci or the angles of the loci, these all become more interesting, and sometimes you even start moving towards the right half plane, or sometimes you remain in the left half plane. So everything depends on this particular system that you have, whether it's a simple one or whether it's a complicated one. Nevertheless, the lessons are the same. What root locus does is it visually telling you where the poles of the system, the closed loop poles that is, where they move and along what trajectory. Now, the example I showed you on the previous slide was a very simple system where we could directly solve for the poles of the closed loop system as a function of k, and very easily show the branches where the poles move along. For most realistic systems, however, this is not possible. You have multiple number of zeros and poles, and a direct solution for the closed loop pole locations is not feasible. In order to plot root locus for these situations, we have to discuss some of the important features that root locus has. One of the most important ones, perhaps, is how many loci or how many branches do I have? In order to answer that question, let's go back to the notion of open loop gain. Imagine I have an open loop gain g times h, which as a generic form, I show it as n of s numerator divided by d of s, the denominator. Let's say the numerator is a polynomial of order m and denominator is a polynomial of order n. If I want to find the poles of the open loop system, the open loop gain, all I have to do is I have to set d of s to 0 and find the roots. Since d of s is an nth order polynomial, its roots will be n values, n numbers. So this system will have n open loop poles. How about closed loop poles? In order to find the closed loop poles, I would have to look into the denominator of the transfer function. And if you recall from the previous slide, this is 1 plus k times g of s times h of s, and I'm actually missing a k here. Let's replace g times h, or the open loop gain, by n of s divided by d of s. So the equation becomes 1 plus k times n divided by d equals 0. Multiply both left-hand side and right-hand side by d of s, and you will get d of s plus k times n of s equals to 0. By solving this polynomial, you can find the closed loop poles of the system. Now, n of s is a polynomial of order m, and d of s is a polynomial of order n. If this is a proper transfer function, which is the case for most realistic systems, we know for a fact that n is going to be greater than or equal to m. This would mean that collectively, this polynomial will be of order n. So if I want to find its roots, I will have n values, which means I will get n poles for the closed loop system. What does that tell me? For a proper transfer function, the number of poles for the open loop gain, the open loop system, is the same as the number of poles for the closed loop system. Now, root locus tries to show me the locations and trajectories of different poles as I change the gain. If my system has n closed loop poles, that means I will have to have n trajectories, n branches, n loci. And you can go back to the example I showed you on the previous slide, and you notice that this was a second order system. I had 2 poles, and my root locus consisted of 2 loci, or 2 branches. If you have an nth order system, your root locus will have n branches or n loci. So that's the first important feature about root locus. Now that I know that I will get n branches or n loci, the next thing that perhaps I'm interested in knowing is, where do these branches start from and where do they end? Let me rewrite the equation that I had in the previous slide. So d of s plus k times n of s equals 0. If I solve this, the roots of this polynomial for different values of k, I will find the poles of the system. Now k, the gain of the controller, will change from 0, or a very, very small number, to a very large number, or infinity. Let's look at both extremes. If k is very small, which is pretty much 0, d of s plus kn of s will consist of one term, which is going to be very, very small, in other words, overshadowed by the first term. So instead of solving for d of s plus k times n of s equals 0, I can just solve for d of s equals 0. And I can say that the roots of that polynomial will be the poles of my system, my poles of my closed loop system, that is. What are the roots of d of s equals 0? Well, d of s is the denominator of the open loop gain. So these will be the poles of the open loop system. What if k is large? If k is large, this term will now be overshadowed by k times n of s. So now instead of solving for d of s plus k times n of s equals 0, I can ignore the first part and just solve for k times n of s equals 0. K is a constant, so I can drop it, and that becomes n of s equals 0. What is n of s? It's the numerator of the open loop gain. So roots of n of s would be zeros of open loop system. So let me backtrack. In order to find root locus for each branch, I will change k from 0 to infinity, and I will see the trajectory of each pole. When k is 0, the closed loop poles of the system, which are the solution to this particular equation, would actually be the poles of the open loop system. So when k is 0, the poles of the closed loop and open loop system are the same. When k is large, the poles of the closed loop system become the same as the zeros of the open loop system. So what does that tell me? My root locus is going to have multiple branches. These branches will start from poles of the open loop system and will end at the zeros of the open loop system. So as I change k from 0 to infinity, my closed loop poles will start moving from poles of the open loop system to zeros of the open loop system. Now, one thing you might ask yourself is, okay, I have m open loop zeros and I have n open loop poles. For a proper transfer function, n is going to be greater than m. So I know that each trajectory will have to start from a pole of open loop system and will have to end at a zero of the open loop system. What if I don't have as many zeros as I have poles? What's going to happen to the poles that do not have any zeros associated with them? Well, those poles will actually go to infinity through some asymptotes. So if you have n poles and m zeros, m of those poles will start from the pole location and will go to the zero location. The other ones, however, will start from the open loop pole location and will go to infinity along some asymptotes. What are these asymptotes? These are direct lines, straight lines that will take you to infinity. All of them will intersect with one another at one particular point along the real axis. That particular point, sigma, is going to be the summation of all the poles of the loop gain minus summation of all the zeros of the loop gain divided by number of poles of the loop gain minus number of zeros of the loop gain. That is where they all intersect, and each of these asymptotes will have a particular angle. How to find the angles? Through this equation. So the angles are going to be 2k plus 1 times pi divided by n minus m. And you will start assigning values to k starting from 0, 1, 2, 3 all the way in order to find those angles. Now by this time, I am guessing that you might feel a little bit confused about what these asymptotes are and how they look like. That's completely natural. Bear with me. In a few minutes, we're going to be doing a few examples, and hopefully those examples will clear up any confusions that you might have at this point. The third and final feature that we will discuss before we get to the examples is whether or not any part of the real axis belongs to the root locus. When I say belongs to the root locus, I mean whether or not any poles of the closed loop system will move along the real axis, either towards infinity or towards one another. So that's the question that we'll try to answer. Now, remember from our discussion earlier that P is a pole of the closed loop system if it satisfies this equation, meaning that K times the loop gain evaluated at that value P has to be equal to -1, which I show it as 1 with angle -180 degrees. This means that the angle of this term has to be -180 degrees. Now imagine that G times H, or your loop gain, is a proper transfer function consisting of m zeros and n poles. So you have zeros starting from Z1 all the way to Zm, and you have poles starting from P1 all the way to Pn. You probably remember that the angle of a transfer function like that is going to be the sum of angles of individual terms in the numerator minus the sum of angles of individual terms in the denominator. So this will be the angle of K times GH evaluated at P will be the angle of K plus the sum of all the angles of the numerator, the angles of P minus ZI's, minus the sum of angles of all the terms in the denominator, minus angles of P's minus P minus PJ's. All these added together and subtracted from one another has to be -180. If you can find a P that would satisfy this equation, that P would belong to the root locus. Why? Because it would be a closed loop pole of the system. Let's consider a hypothetical example. Let's say I have a point P as I'm showing it on this slide, and I would like to know whether or not it belongs to root locus. And again, I repeat, when I say a point belongs to root locus, that means that point can be a pole of the closed loop system, because root locus gives me the locations of the closed loop poles of the system. Based on what we saw in the previous slide, in order for this point P to be a pole of the closed loop system, it has to satisfy this equation, angle of K plus summation of all the angles between that point P and ZI's. Remember, ZI's are the zeros of the open loop gain, minus summation of all the angles between P and PJ's, where PJ's are the poles of the open loop system. This has to be equal to -180 degrees. If that condition is met, P is a pole of the closed loop system and belongs to root locus. Now, let's come back to this diagram. You can see that you can have multiple poles and zeros to the right or to the left of that particular location of interest P. And again, remember that these poles and zeros that I'm showing here, these are the poles and zeros of the open loop gain. Let's consider the zero that I have to the left of point P. In complex domain, if you want to find the angle between 2 points, you probably remember that what you do is you connect them through a vector, and then you find the angle of that vector with respect to the real axis. So if I connect this point here, this 0, to point P with a vector, the angle of that vector with respect to the real axis is going to be 0. So if the angle is 0 in the left-hand side of this equation, it's not going to come to play, so it will have no impact. So any pole or 0 to the left side of P has no impact on the left-hand side, so we can simply ignore those. What about zeros or poles that are to the right of point P? If anything is to the right of point P, if I connect it to P using an arrow, using a vector, I will see that the angle of that vector with respect to the real axis is 180 degrees, which is of course the same as -180 degrees. So if anything I have to the right side of P, then that is going to give me an angle of 180 or -180. These are the poles and zeros that are located on the real axis. What if I have complex conjugate poles and zeros? Let's say I have a pair of complex poles one of them is this guy, one of them is this guy. I connect both of them to point P using vectors, and you can see that if the angle between this point and point P is theta, as I'm showing it here, using geometry, I can see that for the complex conjugate pair, I will get an angle which is going to be 360 minus theta. So if I add those angles together, it's going to be 360 degrees, which is the same as 0 degrees, and again, is not going to count. So what do we learn? The only poles and zeros that matter are poles and zeros that are to the right side of that point P. And how many zeros or poles should I have to the right side in order for that point P to be a part of root locus? Well, let's come back to this equation. When would P be a part of root locus? In other words, when would P be a pole of the closed loop system? If the sum of these angles would add up to minus 180 degrees. Each pole, each zero to the right, will add or subtract either 180 or minus 180. If I have an even number of poles or zeros to the right of point P, the summation of them is going to be either 360 or minus 360, or a multiple of 360 minus 360, which is going to be same as 0. So that is not going to be satisfying that equation. However, if I have an odd number of poles or zeros of open loop gain to the right side of point P, the summation of all those angles would be an odd number of 180 degrees or minus 180 degrees. So only if I have an odd number of poles and zeros to the right, this angle could become minus 180 degrees, meaning that P could become a part of root locus, or in other words, a pole of the closed loop system. So to summarize that, and since my image falls on top of this, let me minimize this so you can read the entire thing. A section of real axis is a part of root locus when there are odd number of poles and zeros to its right. That's the third important feature that we will be talking about. And we will be using these features in order to plot root locus for different functions by hand. Okay, so up until now we have talked about the objective behind root locus and discussed some of the important features along with some equations. Plotting root locus by hand is a very, very simple process if you follow some easy steps that I'm going to be going through on this slide. Consider this example. I have a system with a loop gain of s plus 5 divided by s plus 10 times s plus 1 squared. The first step that I'd like you to do whenever you get a problem is to identify the zeros and poles. So step number 1 is I identify my 0 at minus 5, which indicates that I only have one 0. So the order of the numerator is 1. And my poles are minus 10 and a repeated pole at minus 1. Now in this process, I don't want you to do any shortcuts. So if you have repeated poles, make sure that you write them down individually and separately. I have 3 poles, meaning that the order of the denominator of the loop gain is 3. Now, I have 3 poles and I have 1 0. And you know that the loci or the branches of root locus will start from loop gain poles and will end at loop gain zeros. Since I only have 1 0, that means one of the poles will go towards that 1 0, but the other poles, the other 2 poles, would have to go to infinity along some asymptotes. So the next thing that you have to do is you have to write down the number of asymptotes that will go to 0. Since I have 3 poles and only 1 0, n minus m of those poles, in other words 3 minus 1, which is 2 poles, will go to infinity along asymptotes. So I will have 2 asymptotes. Finally, I will identify the zeros and poles in the S-plane. Let's say I have a repeated pole at minus 1, so I'm trying to show 2 poles here. I have a 0 at minus 5, let's say this is minus 5, and then I have a pole at minus 10. This is our step 1. Step 2, I identify the point at which these asymptotes intersect and their angles. So sigma is going to be summation of all the poles of the open loop gain minus all the zeros of the open loop gain divided by the number of poles of the open loop gain minus the number of zeros. So this will be, I open the parentheses, and again, I have seen a lot of people making mistake in this simple calculation. So I don't want you to do any shortcuts. Go through all the numbers individually. So my poles are minus 10, minus 1, minus 1, minus parentheses, the summation of all the zeros. And I only have one zero at minus 5. Divided by 3 minus 1. So the numerator will be minus 12 plus 5, which is minus 7, divided by 2, which is minus 3.5. Let me use a different color. So let's say this is 3.5 more or less. So this is my point sigma. This is where all the asymptotes will intersect. Next, I will have to find the angles of the asymptotes. So the angles would be 2k plus 1 times pi divided by n minus m, which will be 2k plus 1 times pi divided by 3 minus 1, which is 2. Now you know from previous step that we have two branches that will go to infinity along the asymptote, so you would expect to get two asymptotes. Hence, in this calculation of the angle, you would expect to get two separate phase angles. And the third one, of course, you would expect it to be a repetition. But let's do the math here and see if that turns out to be the case. So if I assume that k is equal to 0, the angle becomes 1 times p over 2. If k equals to 1, the angle will be 3 times p over 2. If k equals 2, the angle will be 5 pi over 2. However, notice 5 pi over 2 is the same as pi over 2, so that's when I have started repeating the angle, so I will ignore this one. So I have two asymptotes that intersect at minus 3.5, and their angles are 90 degrees and 270 degrees. So I will have one asymptote like this, and one asymptote like this. One has an angle of 90 degrees, the other one has an angle of minus 90 degrees or 270 degrees. The third step is the real axis. In order to identify which portion, which part of the real axis belongs to root locus, what you have to do is you have to start from right-hand side and move all the way to left-hand side, looking at the number of zeros and poles that appear to your right. Whenever you have an odd number of zeros or poles to your right, you would consider that section of the real axis to be part of root locus. If you have an even number, that section does not belong to root locus. So let's do it here. I will start moving from here, and as I move along the axis in this direction, I see that I have no zeros or poles to my right, so that will not be a part of root locus. Then I get to this point. At this point, once I pass it to my left, now I have two poles to my right. However, 2 is an even number, so this section is still not a part of root locus. So everything remains the same until I get to this point. At this point, I now have 3 poles and zeros to my right. That's an odd number, so that becomes a part of root locus. So this portion of the real axis becomes a part of root locus until I get to this point. As I move past that point, I will have 4 zeros and poles to my right. That's an even number, so it's not a part of root locus. Now that we know which portion of real axis belongs to root locus, the next thing that remains is to determine how the branches that go to infinity along asymptotes, how do they look like. So I have these two branches corresponding to these two poles, and let me use a different color. So one of them would have to go to infinity along this asymptote. The other one will go to infinity along this asymptote. Now, how do I know about that? Well, these two poles are the starting points of the loci. Remember that each locus will start from an open loop gain pole and will end either at an open loop gain 0 or at infinity. Since I don't have any additional zeros corresponding to these two poles, that means that the loci will start from these poles and will go to infinity along those axes. The last thing that I have to do is I have to make sure that all my loci, all my branches, have directions associated with them. This red one does not, so I have to identify the direction. And again, you remember that each locus starts from a loop gain pole and ends at a loop gain 0. So I start from a loop gain pole, and in this direction I go towards loop gain 0. So this is the root locus of this particular system, and as you can see, it gives you a lot of information as a design engineer. One thing you know is that as you start increasing the gain of the controller, one of your poles will move towards infinity along this direction, the other one moves towards infinity along this direction, and the other one has a little bit of movement from the open loop pole position to the open loop 0 position. However, you do notice that regardless of what gain value you pick, you are not going to have any poles that will cross j omega axis into the right half plane. So the system will never become unstable. Regardless of what you do, your poles, the closed loop poles, are always in the left half plane. Okay, let's do another example. I now have a system whose loop gain is 1 divided by s plus 1 times s squared plus 4s plus 8. What I'd like to ask you to do at this point is I'd like you to pause the video and try to do this exercise by hand based on what we have talked about so far and also what you saw on the previous slide. Once you're ready, hit play and we'll go through the solution. Okay, so I'm assuming that you paused the video and gave this a shot. Let's see how the root locus is going to look like. So what I'm going to do is, based on the steps that I discussed last time, I will start with step 1, which is identifying the zeros and poles. So I don't have any zeros, so I would say I don't have a 0. So the order of the numerator is going to be 0. How about poles? Poles are -1. And I have a complex conjugate pole here, which is going to be -4 plus minus j square root of b squared minus 4ac is going to be 16 minus 32, which is 16. And instead of square root of 16, let me erase that and write down 4 divided by 2. And again, perhaps it would be a better idea to simplify this as -2 plus minus j2. So let me go ahead and erase this and write down -2 plus minus j2. I have 3 poles, so the order of the denominator is going to be 3. Next thing I have to do is I have to identify how many branches will go to infinity along the asymptotes. The number of branches that will go to infinity would be equal to the difference between the poles and zeros of the loop gain, which in this case is going to be 3 minus 0, which is 3. So 3 branches will go to infinity. That's step 1. And of course, I would need to identify the poles. So let's say if this is 1, and this would be perhaps -2 plus j2, and this is -2 minus j2. All right, step 2. We identify the points at which the asymptotes intersect. So this point sigma, I'm not going to write down the equation anymore. I'm just going to be directly plugging in the values. So I have a parentheses, the actual values of the poles. I have a -1, a -2 plus j2, and a -2 minus j2. I don't have any 0, so I can just leave a 0 here, divided by 3 minus 0. j2 cancels out minus j2, so I will have a -5 divided by 3. -5 divided by 3. This is where the three asymptotes will intersect. Let's say minus 5 divided by 3 is more or less somewhere here. So that's my sigma. Then I have to identify the angles. So the angles for these asymptotes are going to be 2k plus 1 times pi divided by 3 minus 0, which is 2k plus 1 times pi divided by 3. Notice I'm not doing any shortcuts when I have an n minus m in the denominator. Despite the fact that I know m is 0, I still write everything out. So I don't try to do any shortcuts because it's very possible that you may make mistakes here. So 2k plus 1 times pi divided by 3. If I set k to be 0, that will give me an angle of 5 over 3. If k is 1, it will give me a 3 pi over 3, or pi. If k is 2, it will give me a 5 pi over 3. These are still different angles. If I give it a number of 3, however, I will get 7 pi over 3. 7 pi over 3 is the same as pi over 3, so I ignore that. And I will have 3 separate angles, and that makes sense because I have 3 poles that go towards infinity along the asymptote, so I only have 3 asymptotes. The third step is going to be looking at the real axis. So what I do again is I start moving all the way from the right to the left, and I see how many poles or zeros I have to my right. Here I have nothing to my right, so it doesn't belong to root locus until I get to this point. When I get to this point, I start having 1 pole to my right. So that means this portion is a part of root locus. It is a part of root locus until I get here. Once I pass this point, how many poles would I have to my right? Well, I have the 1, which is on real axis, and I have the complex conjugate pair. So that's 3, still an odd number. So this portion continues to be a part of root locus. And after the complex conjugate poles, nothing really happens. So I would actually have the entire axis to minus infinity to be a part of root locus. Finally, I would do the asymptotes. So one of the asymptotes has an angle of 60 degrees. Let's say this is 60 degrees. The other one has an angle of pi, which is somewhere here, pretty much along the real axis, and the other one has an angle of 5 pi over 3, which is 300 degrees, or minus 60 degrees, which is going to be somewhere here. So now that I have my asymptotes, I know that 2 of the poles will move along those 2 asymptotes that have angles of 60 and minus 60, and the other pole will move along the third asymptote. This pole that I'm showing with the red arrow, this is the pole that, if you notice, it is actually going towards infinity along the real axis, and real axis itself is an asymptote, so this is already taken care of. The other 2 would have to go to infinity along the other asymptotes with 60 and minus 60 degree angles. So one of the poles will go to infinity like this, and the other one will go to infinity like this. And notice both of them are along the asymptotes. And lastly, for that portion of real axis, I would have to assign a direction, and notice the locus starts from a pole and goes towards infinity, so the direction is going to be from the pole to infinity. And let me make these lines a bit thicker too so they stand out. So these are going to be the directions of movement to infinity. And again, if you notice at the root locus here, you see that this is a third order system, so as you change the gain of the controller, these poles start moving around. However, compared to the previous example, you notice something interesting, that one of the poles, which is the one I'm showing in red, that one will stay stable. By increasing the gain, it'll move along the real axis, and it actually becomes more and more negative. However, the other 2, at some point, you can imagine that these asymptotes will cross the j omega axis, meaning that the poles will creep into the right half plane, and hence this tells you that for this particular system, if you increase the gain beyond a certain threshold, two of the poles become unstable and will go to the right half plane, so the entire system becomes unstable. So this is the root locus for the second example. Okay, let's do another example. Imagine you have a system whose loop gain is s plus 1 divided by s plus 2 times s plus 3 times s plus 4. And this, in fact, has to be example 3, not example 2. Again, I would like you to do the same thing. Please pause the video at this point. Try to do this by hand, and once you're ready, hit play to see the answer. Okay, let's solve this root locus. So step 1, as before, I identify the zeros and poles. I have 1, 0 at -1, which means that the order of the numerator is 1, and I have 3 poles at -2, -3, -4, meaning that the order of the numerator is 3. I would have 3 loci, 3 branches that will start from loop gain poles. One of them will end at a loop gain 0, pretty much the only 0 that I have. The other 2 would have to go to infinity along asymptotes. So the number of branches that will go to infinity along asymptotes will be n minus m, 3 minus 1, which is 2. So 2 branches will go to infinity. Let's identify the zeros and poles here. So let's say this is -1, so that's my 0. I have a pole at -2, a pole at -3, and a pole at -3. Step 2. Now that I know that I have 2 asymptotes, let's find out the point at which they intersect. So sigma is going to be summation of all the poles, which is -2, -3, -4, minus summation of all the zeros, which is -1, divided by n minus m. The numerator is going to be -9 plus 1, which is -8, divided by 2, which is -4. So that's my the point where the asymptotes will intersect. How about the angles? I know that I have 2 asymptotes, so I would expect to see 2 independent angles. However, I can just do the math and see when the angles start repeating themselves. So I will have 2k plus 1 times pi divided by 3 minus 1, which is 2k plus 1 times pi divided by 2. If I assign k to be 0, this will give me pi over 2. If I assign k to be 1, it will give me 3 pi over 2. And if k is 2, it will give me 5 pi over 2, which is the same as pi over 2, so I ignore that. So I will have 2 asymptotes, one of which is going to be having an angle of 90 degrees, the other one 270 degrees, and they intersect at -4. So this is going to be one asymptote with angle 90 degrees. This is going to be the other one with angle -90 or at 270, and of course that is going to be my point sigma. Notice that sigma ends up being actually the same location as one of the poles, so it's at -4, which is one of my pole locations, and that's okay. Step number 3, we will look into the real axis and try to determine which portion of real axis belongs to root locus. So I will proceed the same way. I will start moving from right hand side to the left hand side and see where I would have an odd number of zeros or poles to my right. At this point, I don't have anything to my right, so this is not a part of root locus. Then I start having 1 to my right, so this becomes a part of root locus until I get to this point. After this point, I will have 2 zeros and poles, or in other words, 1 0 and 1 pole to my right, so that's an even number, not a part of root locus until I get to this point. At this point, once I start moving to the left, I will have 3 zeros and poles to my right, so that will become a part of root locus. Next, I would have to find the branches that will go to infinity. And notice, this is actually an interesting problem because you notice that 2 poles are kind of moving towards one another. Remember that in root locus, you're dealing with loci, And these loci will indicate in what direction the poles are moving. Each locus, each branch will start from a pole and will go either to a 0 or to infinity. This one is pretty simple, so I can easily find the direction. I start from the open loop pole and will go to the open loop 0. How about the other two? This is a little bit tricky. So you have to understand that the direction of the poles would actually start moving away from the loop gain pole location. So I will be moving away from this pole location and moving away from this pole location. At some point, I am bound to make a connection. So both of these will hit one another at some point. This is going to be a break point, but we're not really interested in calculating exactly where that point is located. All we know is somewhere between -3 and -4. At that point, one of the branches or one of the poles will go to infinity along this branch, and the other one will go to infinity along the other asymptotes. And this is going to be the root locus of the system. And notice again, in this case, similar to the first example that we did, regardless of what gain value you choose for your system, the system will always remain stable because the poles will never creep into the right half plane, and they always remain at the left half plane. So hopefully with these three examples, things have become a little bit clearer about how we plot root locus by hand. Again, let's have a quick recap of what we talked about. Root locus is a tool that allows us to assess the locations of the closed loop poles of the system once we start changing and varying the gain of the controller. It shows us if the system remains stable or goes unstable. And as we will see later on, it allows us to see, for example, what the transient behavior of the system is going to be.